Today's demonstration will be a tensile test performed on a polymer sample inserted into an Instron servomechanical testing frame. The testing frame uses Blue Hill software to record all data and run. Dimensions of your sample need to be measured and recorded. The gauge length of the sample along with 3 values of the width and 3 values of the thickness need to be all measured. The values for the width and thickness need to be averaged together for 1 value each. Machining of the sample can cause slight variances in these dimensions, and that's why we average them out. All of your dimensions need to be recorded in a notebook for later viewing. Often after turning on your testing machine, the load display will record some sort of value as being acted on the load cell. This requires us to go up and balance out the load cell and bring it back down to a 0 value before running any tests on any samples that you would plan on doing. After balancing out your load cell, it is now time to place the sample into the machine. Oftentimes the crosshead is not in the correct position for your sample size, and this requires us to adjust it accordingly. Once the crosshead is in the right area, we place the sample into the machine, tightening the collet grips on the lower end first. It's important to tighten them in a uniform manner so that extra deformation on the sample will not occur before the test has even been run. Once the sample has been tightened down in the bottom collet, we can then adjust the top and fine-tune it to the right size of the sample, in which then we will start to close the top collet. The method in which the grips actually tighten down on the sample will put the sample in a compressive load. To keep the sample from deforming before we want it to deform and have run our test, we can manually go and adjust the height of the crosshead to take the sample out of compression and lower any load that has been placed on it back down to 0. With the sample experiencing 0 load, we can now place our extensometers onto the sample. The first extensometer is an axial extensometer and measures the axial strain the sample undergoes during the test. It's held on with rubber bands on the top and bottom legs, with each leg having a sharp blade that's touching the sample surface. Any extra adjustment of the extensometer when it's touching the sample can cause surface defects, which in turn can cause premature fracture. Once placed onto the sample, we can remove the safety pin and the extensometer is ready to measure. The second extensometer is a diametral extensometer. This will measure the change in width of the sample as it is put in tension or compression. Once the extensometers are placed onto the sample, we need to balance out the readings for the transverse and the regular strain. This is done by going up to each channel that the extensometer is connected to and clicking on the balance option. In today's test, we'll be loading a polymer sample in tension up to a final value of strain and then unloading it back down to 0 force. If we look at our strain time plot above, the AB segment is our loading segment. This will be performed under strain rate control at a rate of 1 times 10 to the negative 3% per second, or a tenth of a percent of strain per second on our polymer sample. This will be controlled through our axial extensometer. The axial extensometer tells the machine whether to add or subtract force on the sample so that we have a constant rate of deformation achieved. The B value will be our final value of strain and is chosen as 4%. This is chosen based on material behavior and lies within a quasi-elastic region of our polymer sample. Quasi-elastic means that we get some elastic behavior, but at the end, some plastic deformation is experienced. The quasi-elastic region, though, does tell us that we should not experience fracture due to over-deformation of the sample. The BC segment is our unloading segment and is unloaded at a negative 1 times 10 to the negative 3% per second, or a tenth of a percent per second in the negative value. Instead of unloading our sample down to 0 strain, we're loading it to 0 force. Because we're in the quasi-elastic region, we're expecting some residual strain left over. If our material performs perfectly elastic, 0 force will result in 0 strain. But like I said, we're expecting some sort of residual strain left over. If we were to unload to zero strain, we probably would place our sample in compression. The stress-strain curve below our strain time plot is a general depiction of the behavior we're expecting out of our polymer sample. We will get an increase in stress all the way to our final value of strain, and then we'll have an unloading from B to C and a decrease in stress, showing some residual strain left over at the C point. This is a screen capture of our test profile under the Blue Hill software. The outlined box on the left is our loading ramp. As you can see, we are in a tensile strain mode, like I explained, with the extensometer being the control. We have set a percent of 4% strain as our endpoint, and we have our loading rate at 0.1% per second. The box on the right, which is now highlighted, is our unloading segment. We are still in the tensile strain mode, but instead of setting a strain endpoint, we've set a zero force endpoint, and it's controlled by force control. We have also kept the same rate, but placed it negative so that we will unload instead of continuing to load. Here we see a screen capture of our data collection control. It's important to note that you do not want to take too many data points when performing tests. Oftentimes, taking too many data points will give you a distorted output on your plot, giving you a false sense of what's actually occurring in your material sample. When we look at our screen here, we can see that we're set to take a data point every 10 seconds or every change in 10 pound forces. Safety limits can be put in place to stop the machine or throw a warning signal to the user in case something goes wrong. Today we'll put a safety limit on our extensometer for a maximum and minimum strain. Anything over 4% will stop the machine because we've overextended our sample, and anything under 0 in the negative value means we put it in compression. We can also put them on the load cell for a maximum and minimum load. Anything at extremely high loads means something in the test has gone wrong, and again, a negative load means that we put our sample in compression. Safety limits can also be placed on extension and the diametral extensometer if need be. A physical safety limit can also be put on the machine where the crosshead moves up and down. These yellow sliders can be adjusted to make a safe zone of movement for the crosshead. We can put a maximum and minimum distance that we want the crosshead to move up and down, and anything past these distances will stop the test. This will keep our extensometers and other equipment safe from overextension and being placed in situations in which we don't want them to be. Now it's time to start our test. This is a split screen view of the sample on the right, and then on the left the computer screen plotting out the data points during the test. Keep an eye on the plot as it begins to take form, and also at the load values and the axial and diametral strain values. As we near zero load, watch to see if there's any residual strain left over, or did our material act perfectly elastically. This concludes our demonstration on how to set up and run a tensile test on an Instron servomechanical testing machine.